Okay, let's look at a slightly different problem. Okay, so 3 dimensions now. Let's say we had a cylinder. So a cylinder is characterized by 2 dimensions, its radius and its height. We can write down the volume of a cylinder. So the volume of a cylinder is equal to the area of the cylinder times its height, just as with any prism. So pi r squared times h. And let's say that we know that r and h are constrained in some way. So let's say r plus h equals 6. Okay, so there may be constraints, for example, in a shop. You may want to have objects of a certain size to fit nicely on the shelf and to pack them in the best way. You could imagine this is a toilet roll and you're trying to fit as many toilet roll onto the shelf so that there's enough for people to go in and buy and that nobody will run out. So V equals pi r squared h. Let's use the constraint equation again to write this in terms of just a single variable. Now we could do either. We could either replace h or r here, but because we've got r squared, it's easier to replace just the h. So from here we can see that h is equal to 6 minus r. So V is equal to pi r squared times 6 minus r. If we multiply this out, we get 6 times pi r squared. And then we've got minus r times pi r squared, so that's minus pi r cubed. Okay, and this is V. And now V is written it just in terms of r. We've eliminated h. And it's always going to be that same technique. We're always going to use the constraint equation to reduce the thing that we're trying to minimize or maximize, in this case the volume. We need to get that in terms of just a single variable. So now we can differentiate. So I'll just use prime notation. So V primed is equal to, so the 2 comes down to the front, 12 pi r. And here the 3 comes out at the front, reduces the power by 1, so minus 3 pi r squared. And that's going to be equal to 0. Now if we solve this, let's just factorize it. So we got r times 12 pi minus 3 pi r equal to 0. So either r equals 0 or r is equal to 12 pi over 3 pi, which is equal to 4. And if r is equal to 4, then h is equal to 6 minus 4, which is 2. So the dimensions of the cylinder, which give you the maximum volume, if this is how they're constrained, is that the radius is 4 and the height is 2. What volume would that give? So volume is equal to pi r squared h. So this is equal to pi times 4 squared times 2. 4 squared is 16, times 2 is 32, so the volume is 32 pi in whatever units we have cubed. Okay, so that may be meters cubed, centimeters cubed, if you're a chemist, decimeters cubed. Okay, there we are. Now, we've said that we've maximized that, but how do we know it's a maximum? How do we know it's not the minimum? Well, what we can do is we can then find the second derivative. Okay, so the first derivative was this, 12 pi r minus pi r, 3 pi r squared. So if we differentiate this again with respect to r, we get 12 pi minus 6 pi r. And now we'll check our solutions. Well, first of all, let's check r equals 0, because that was a solution as well, but we said nothing more about that. So let's put that in here. So we have v double primed at 0 is equal to 12 pi. Well, in this term will be equal to 0, so it's just equal to 12 pi. Now that's greater than 0. So if the second derivative is greater than 0, what does that mean? It means that this is a minimum point. And that should be obvious. If they've got a cylinder with 0 radius, then you're going to have 0 volume, which is obviously the smallest you could have, and it's not not useful in any way. Let's try the other one. So the other solution that we found was r is equal to 4. So we have 12 pi minus 6 pi times 4. So 6 times 4 is 24, so this gives us minus 12 pi, which is negative. And therefore, as we've claimed, that's a maximum solution. Okay, and that completes the problem.